Hi, Professor. This is Avik here. Currently, I am in my master's in Material Science and Engineering in National Institute of Technology, Trichy, India. So, at present, I am doing my master's thesis in Indira Gandhi Center for Atomic Research. So, a few months back, I contacted Professor Stephen Cottenier for doing a project on how do grain boundaries affect the strength of tungsten alloy in fusion reactors. So currently I am in Indira Gandhi Center for Atomic Research. I am working on kind of same project. It's studying the workability of titanium modifier austenitic stainless steel in nuclear reactor. So titanium modified stainless steel is not used for much more time here. So there were some tests which were going on in on this material for tension and compression purpose. Right now we are doing this test in tension. Right now we are doing this test for torsion. So before that, I want to tell something about this Indira Gandhi Center for Atomic Research. So it was established in 1985 by Department of Atomic Energy for developing this first breeder reactor. So in this first breeder reactor, it is like a three-stage plan. So in the first step, it will be doing this power generation from natural uranium. In the next stage, this natural uranium will be giving plutonium, which will be used with the thorium to get this uranium again. And in the second stage also, during this process, this first breeder process, the electrical power will be generated, and in the last stage also we can get electrical power from this uranium. And after this also, the waste material can be used for weapon purpose or some other purpose. So in this process, in this first breeder reactor, this wastage will be much less than any other nuclear power plant. So that's what the plan here for Indira Gandhi Center for Atomic Research and vision and mission, whatever we can say about this Indira Gandhi Center for Atomic Research. So currently, if I come to my work, before that I will be having some notes so that I don't miss anything, whatever I want to say now. So this titanium modified austenitic stainless steel is a structural material for this nuclear power plant, which you can use it for cladding and wrapping for this nuclear fuel in the fuel pin. So earlier we were using this 316L or 316Ln steel for this purpose, but for this much more void soiling capacity, and for this titanium modified stainless steel and the creep resistance for this titanium modified stainless steel make us using this material for future purpose. So there has been a lot of work from Indira Gandhi Center for Atomic Research on this material. So there are a lot of data are also available for tension and compression testing, because these two testing were done before. Right now we are testing it for tension purpose, so that in this bulk workability it can be used, how much it can be deformed or all these things. So in this current, the reason for doing this checking this torsional behavior is basically because this torsional behavior can give the deformation of a material for a very high strain and strain rate. For compression, if we see, we can't deform a material more than 100%, because that is not logically or theoretically possible. But for tension also, it will be up to 0.3 to 0.7, and after that the material can fail. And material generally fails after that. Any steel component will fail after the strain of the 0.3, in between 0.3 to 0.7. But for tension purpose, we can deform this material for very high strain and strain rate, both the things. So right now in my project, what we are doing, basically it will be high temperature tension testing, beginning from 700, 800, 900, 1000, 1100, and for the strain rate will be like 0.01, 0.1, 1 and 10 right now. And if you get time, we will doing it. We will be do much more after that. So what we are telling, like in bark workability, in any massive forming like forging, like extrusion or rolling, the strain rate is very high. So that we need to use this torsion testing to know how the material will be deformed in that strain or strain rate in high temperature. So we are doing this for that purpose, and the newly installed machine from Bangalore based company, so that is giving us the exposure to do all those kind of testing on this same in this titanium modifier austenitic stainless steel. So uh, so this will be basically my experiment, and after this experiment we have to do this microstructural analysis and many more things computationally and also experimentally, like seeing this material how it is getting deformed in this high tension rate, high strain rate in tension. So next my target will be, after finishing this like you can say this baking of material, what my target will be like after that is, like along with this experiment I will be doing many metrography for this broken specimen. Like first we have to check this microstructural evolution in this high strain rate. So like in 1100 degree in a certain strain rate, like in 1100 degree this 0.01, if we give a 0.01 strain rate, the size of the microstructure or the size of the grains will be much more bigger than if we deform it in 700 degree or room temperature. So those are the things we have to map it with the temperature and strain rate to this microstructure evolution. So that's a kind of a work we are planning here. So if possible we can do a lot of mechanical interpretation also to these experiments, because we can check in how much tension or how much strain angle or how much torsion angle, or we can check at how much load the microstructure keep on deforming. It's getting a different shapes. So we'll be doing this strain rate till point 01 to 10. So along with this experiment I will be doing many this metrography of this broken specimen. First we have to check this microstructural evolution. The samples were actually, before using these samples, the samples were heated up to 1100 degree. That's called this annealing thing were done to this material before you use it for our purpose in before you use it for our purpose in this torsion testing. So microstructural evolution it was giving a very equiaxed microstructure of this material. So after deforming it, along with this experiment I will be doing many metrography for this broken specimen. First the microstructure evolution. First part will be the microstructure evolution, how the microstructure get evolved with this different strain rate and temperature. And next the samples were before using the samples to my experiment, the samples were heated up to 1100 degree. So this experiment I will be doing metrography for the broken specimen. So first the microstructural evolution. First we have to check the microstructural evolution. Then the samples were heated up to around 1100 degree centigrade before this experiment, what we call this annealing thing. So in this annealing we got this microstructure in a very equiaxed form. Near this radius, it was actually giving almost equal size of this, equal area of this all the grains after this annealing. So next, so along with this experiment I will be doing metrography for this broken specimens. So first we have to check this microstructure evolution with different temperature and strain rate. So the samples are heated up to around 1100 degree before this experiment, so that we can anneal it and get a very equal and very regular microstructure for this material. So after doing this annealing, I have the microstructure available. It was almost, the area was almost same for all the grains in that microstructure. So next, after the test, what we expect generally is like this. During this torsion testing, the area of the grains will be much more bigger at the side of the radius, and it will be smaller in the radius portion. So that's what we got earlier also. So I hope we will be getting the same kind of results in this experiment also. So besides this, we have to go for studying this fracture surface in scanning electron microscope. So we can study the torsional surface, the broken surface from this scanning electron microscope, and after understanding this for the dislocation, so during the failure the dislocations happen. So this dislocation movement, the dislocations type, what we can measure it from this positron and annihilation spectroscopy, which is available here. So I'll be doing that part also. And earlier we observed some serrated flow in this material. So what is the serrated flow actually? So what happens in a stress strain curve of any material is like it will be a clean straight line till it yields, and after it start yielding, the pattern will be, from a bigger perspective, if you see it from a distance, it will be shown like it's regular. It's going to a yield point, and then it's going to a ultimate point, and it fails. But if you practically go a bit nearer to this thing, what will be happening? It will be very regular pattern of up and down, like it will be a bit curvy pattern for this stress strain curve. So after reaching this, after reaching the critical strain for any material which is going to failure, so going to any mechanical failure like tension or compression or whatever it is, or torsion it is, so what it will be showing a very erratic behavior. So it will be like a bit linear, and it will be like up and down. So that thing is, we called it the serration effect. So there are many theories behind this serration effect. So right now I want to study this serration effect under this Anantakrishna model. So Anantakrishna is a professor of Indian Institute of Science in Bangalore, India. So they gave a model of this serration, and I will be doing my studies, and I will be trying to match my data to this to the same model. So next, besides this experiment, I